I'm going to wait just a second with introducing myself and say the topic, as you see, is we want to talk about GRC brick facing claddings. We have two different solutions that we offer to the market now. So this presentation is very much about seeing, well, the technology that we chose to go for and why, and some potential benefits that we see out of them. So it's not like it's accurate science, it's just based on our thinking, rationale, and test what we think is the best way to offer this product to the market. Just briefly, allow me to talk about BB Fiberbeton. I know Peter Reed mentioned some details, but yes, it's a family-owned business. It was established in 1984. We have in-house design and drawings, including structural design, in-house mold making, and we only do bespoke GRC. Only GRC. We don't have any UHPC, no precast, no nothing else. We want to be very good at making GRC and all the things that are tough to make. That's what we like doing. Just very briefly, the company in 2014, there was an ownership shift over a few years with Nikolai and Simon stepped into the ownership. And after they did that, they observed probably, and a few years later, they just begin changing and improving, and they are hungry to make things better and more innovative, more efficient, and so on. So the whole company has grown through the last few years into a pretty sizable company that produces around 100,000 square meters of GRC per year. We just increased our capacity, and we already utilizing a pretty big part of that. We produce in Denmark, we produce in UK, have around 140 employees, and we are a full member of the GRCA. I know this is a strange thing, but I like knowing who is actually talking. I hope you also appreciate that. So it's not to have a selfish promotional spot. It's just so you have an idea of who I am. But of course, I need to mention everything you do, whatever you do, you innovate, whatever we create in a company is a team result. I have a fantastic team. I mean, our group is just perfect place to spare and coach each other and so on. And people love bringing ideas. So of course, everything I'm bringing here is a result of a company, not me, but physically I am here. So I will let you know that I am the head of development at BB Fiberbeton. I have a civil engineering master's, a PhD. I have been a totally nerd for concrete my entire life. I mean, that's the only thing I have been touching from all kind of angles. I love concrete. And I did that for 19 years until I figured out that, well, maybe those guys in Denmark that were doing GRC, that was the funniest thing to throw myself into. And luckily, I got that position as well. So before then, I joined the GRCA. I'm a member of the council. I've been there since 2016. And I joined BB Fiberbeton since January 2021. Now I'll get into other stuff. Well, just some general writings, I guess all know, and of course this is regional dependent, but there are many regions where masonry brick is just, associated as that is a quality house. People like masonry look, they want things in masonry. That is the custom, we're sticking to what we know and we did and has a certain image that we like. So of course, we also have to have a solution for this global industrialization in the GRC business. We need also to be able to do that efficiently, keeping the important things that we have in GRC, which is the low weight, low material usage, and all these gains that we have. We have to have a smart solution that keeps selling GRC for its good things. We cannot do just GRC, 4 times more heavy than take precast. It's going to be it's going to be a cheaper option. So that's the reason why this presentation is that there are some things that we would like to challenge a little, and we chose to challenge because otherwise we don't believe we are matching the needs that GRC needs to offer to the market. Then it's just a product without really a potential in the market. Again, sustainability. Yesterday, nobody spoke about it until the panel discussion. Now everybody's speaking about sustainability. I will, of course, also have the sustainable side in this presentation because at the end, you need to have that. I mean, we are at least where we are, the markets that we are serving, they are asking for it, and they are asking for it increasingly. And I hope all suppliers will help us improving the quality of the EPDs and so on of all your materials, because that is what is going to make sure that we have a business in the years to come, an increasing business. We want increasing business for all of us. So of course, we believe there are some new challenges that maybe has been too simplified. So we are trying to, before going and launch everything, we sit down and let's think about this very thoroughly and make sense out of it. I think, personally, things need to, first of all, make sense from a physical point of view. Before testing anything, you need to think, does it make sense what you're doing? Second, of course, you need to prove by tests what is the material that you are actually bringing to the market. So you can show somebody that your thoughts actually had some kind of ground. So again, in the paper you will see more deep, you can go very much deep, there's going to be a lot of stuff. Please focus on the headlines and then you can go into details afterwards. But of course, I'm going to just present the principles behind it, what thoughts we had and why we went going that way. And of course, all of that will also have a kind of a sustainable side, so the relative environmental impact of going one way or the other is going to be part of the presentation. Sorry. First of all, there's two solutions I'm going to talk about. One is the brick slip. I mean, cut regular bricks, and then we have it on a GRC panel. I will go in details on how that works, or we chose to make it work. And then the other one is where why use the bricks? Why not make it GRC all the way through? And that's going to be the one that we finish up with. But first I'm going to go to the more traditional, the one we know. We buy some slips and we try to make GRC elements out of that. Just to show some examples of what we can do with this brick slip solution. This is just the left side is a panel that we have installed in our factory. We were testing both the connection, to keep it closed from water. How does it look to make it more elegant than just one line with some acrylic or whatever rubber product inside. And on the other side, the amazing thing about GRC, and that's again going back to let's remember what GRC can. GRC is low weight. It can go into a low weight facade. If I suddenly make a 100 kilo per square meter panel, it's not going to be able to put or install on a timber construction row house or load bearing construction. And I don't know how it is in your countries, but we are experiencing a lot of that tendency. Many architects, all of them, want to prove that they also can manage, zero emissions based on wood, and they can make it last and everything perfect and get the nicest prices and so on. So of course, we also have to think it has to be something that we can put on something that will not take a very, very heavy load on the surface. So just to give an illustration, we are trying to move within all of them. I mentioned some CO2 equivalent, if you can, so this is the A1, so the cradle to gate emissions of that particular element. Don't hang so much on the numbers itself because it depends on the EPD that you will get from your brick supplier. It will, of course, depend on your own EPD. It will depend on the EPD of the bracket systems, whatever we have chosen to hang it up with. But for this specific element, made with those specific materials, that is what we could offer and tell the client you're buying that number. The same if you go to this one, that would be the 27 kilo per square meters. It's good to keep it on your mind because I'm going to go through some others that we can compare with later on. So what we do is no mechanical fixing. That is, and I will go more into that. We want to settle for 100% direct bond. That is what we believe is the only way to really handle the situation. We pre-treat our bricks, of course, to ensure that we get that bond. And we offer to clients, as anybody would do probably, is you can choose colors and textures of your joint systems as you wish. If you want pink and you want with visible aggregates, we can make that. That's no problem. So that's what we want to do. We want to, as much as possible, match whatever an architect wishes to have. One of the reasons why we want to go this way is because we assume that bricks will, during service life, crack. We are not trying to tell ourselves that they are super bricks, they will last forever, they will never crack. But what we're going to say is that since I don't get any mechanical properties, and if you look at publications, what are the mechanical properties of bricks? It's going to be everything from A to Z. All producers have different formulations, different kind of products, and within their own production, different techniques and so on. So the information that you actually need, if you want to account for that from a structural calculation point of view, is not available. So that's what we start with saying, since we don't have that, we need to find a system that holds the brick regardless of whether it cracks or not. Whatever happens to it, it has to stay on site. So as I mentioned, the goal is to make sure that the bricks don't fall off. We don't want to hurt anybody. I guess also that is the purpose of a mechanical fixing. So we have the same purpose. So the core challenges when we were doing this is, of course, the warping of the elements, the composite behavior, understanding what happens when you play with this, with the thicknesses of them and so on, and the bond between brick slips and the GRC. Of course, that is the whole point of the system we have chosen to do. So we need to manage that 100% properly. So the warping, if we go to the warping challenge, well, actually, you are combining something that is inert, is dead. A brick is dead. So then I put concrete behind. It's a wet mixture that immediately likes to begin to react. When it reacts, you have a chemical shrinkage. You can control it up and down and so on, but there will always be a shrinkage. Then you will always have a practical point of view. You're finishing your element and so on. Some water is being evaporated. You're removing mass per volume unit. That means the concrete will contract. So what happens? You have a nice bow if you don't do anything. That's the only solution. That's the only thing you can get out of combining these two materials unless you do something to counteract it. So what we did is, of course, do a lot of tests. We thought it must be related to the cross-sectional area of your element and so on. We do have the tolerances that we use for our own elements. Let's say, okay, let's try to calibrate a model. Let's build the other model. So whatever geometry somebody brings to us, we are able to quantify. We need these ribs, we need that. They're so high, so much mass, etc., etc., etc. So that was what we did with all the tests. We believe we are there. At least we are succeeding when we do the big elements and so on. So that was one of the goals to achieve. Secondly is to understand this behavior between brick and a concrete, and a GRC, or a concrete. I mean, it doesn't matter really. The thing is just that in precast concrete is so massive, the concrete behind, that the warping is never going to happen. It cannot happen. It's so strong. We are just not that big in terms of volume of concrete. So there is some tensile strength properties of the brick slip, 0.75. And again, I tried to look up. I found all values in the world you could imagine when you look for tensile strength of a brick. It's not something is documented, but some researchers have done something. So the value that I chose to do is the one that I actually measure when I try to break myself one brick. So it's 0.75 megapascal for the 5 types of bricks that we have played with. I will not say that there are some that go up, down. That's not the topic. But for this specific, the one that we were playing with, that was the value that we measure ourselves. Then we have a grade 18 GRC, a polymer GRC, 11 megapascal. That is our measured tensile strength of our product. So you can see there's a pretty big factorial difference between these two products. Then we have a compressive strength. It's not going to be that actual, but there is a big difference. One is very brittle, the other is ductile. That is what we're trying to, at least in the early ages, there's a lot of discussions, but I mean, ductility in the early ages is also relevant for these purposes. So what I'm going to show is just, there's going to be we made some finite element simulation, so structural calculations with nice software and so on, just not to try to quantify by decimal is exactly this, but is to understand if I do this, what happens? If I do that, what happens then compared to that? Just to try to understand. So when you see some figures in the next slides, there's going to be some red colors. That means that when I have made a panel and designed it according to the guidelines for design of GRC and utilizing the load-bearing capacity of that GRC that I'm projecting, where will I have a tensile stress above 0.75 megapascal? That in our bricks means that it actually cracks. Somewhere there's a crack, at least, when you reach to that. The first we start with is just a brick slip with 15 millimeters and 12 millimeters of GRC behind. And we're also only looking at suction because, of course, if I push to the element, the tensile load is on the GRC, which can take the tensile load, whereas when I suck or I pull the element, I get the tensile strength to be on the bricks, which are the ones that cannot withstand the tensile stress. So what happens is that you see the entire brick almost in this setup that I try to sketch. The entire brick's cross section is above 0.75 megapascal. So there's no way that is not going to crack. And you can see also if you look at the cross-sectional area, we have the same. You just have your grout, or depending on the strength of your grout, you will go down to the fiber. So you will have a bridge overlapping through the jointing system. So when looking at where I have exceeded the tensile stress of the brick, there is no single point mechanical fixing that can make sure that my brick slip doesn't break or crack. Because it's not only where I place that, it's everywhere in that brick. 3 minutes too long. We did the same change. If you increase the thickness of the brick slips, then you're getting the problem in the connection in the corners, so where the brick slips meets the GRC, so it's trying to separate. If I go the other way around, I increase the GRC thickness, I just get even more load on the cross-sectional, even down to the tensile, to the flexure strength. We did just a small test just to see what happens when we really try to load. Let's see. Just because you don't see a crack, it doesn't mean that there is no crack. It just means that the crack is not big enough to be of any concern, because cracks are supposed to be in concrete and everything. So this is actually just showing that when we do this 4-point bending loading system, we can see the first crack around 70% of MOR. And you can see what basically happens is that since I don't have a mechanical fixing, I have the behavior I want. Once it begins cracking, you get another crack, you get another crack. So I get millions of small cracks instead of having one big that is acting as a bridge. That's what the target we wanted to achieve. I'm speaking way too slow or having too much content. This is just trying to schematically have a look at the paper because it's just what I tried to say, but just schematized. So how do we see it would work under a pure bond, under a threaded rod, or an embedded filament as a bond, and our pros and cons and worries. But anyway, the conclusion for us is that we don't see any other way that you are selling a false sense of safety if the mechanical fixing is your only strategy to keep that brick in place. So we don't want to do that. Anyway, the last thing is that we need to make sure that the GRC bond sticks well. So we made many panels, we cut them. We were even hard to ourselves. I see some people that test for the whole brick, but there might be some interlocking in the grouting that helps keeping the brick in place. So we don't want to do that. We do like the porcelainic guys, the tile guys. We cut them and we make sure that we make a pull that has absolutely no geometrical constraint. We're making a direct pull of the connection in between those. All of them we've sent both to our own laboratory, UK accredited in UK, and we also sell it to our cement supplier, to their laboratory. So we made it over several. Let's get it measured by different people to find out that it's safe. We are concluding rightly. So all of them, we got this pull-out strength of 0.67 to 0.74 megapascal. We do some weathering tests. Again, there is no real test to find out. We are still lacking to measure the pull-out strength. But what we did is we did some existing tests and then visually see, is there any cracking? Is there any things that seems to be leaving? Is the brick loosen up and so on? You're very stressing, Peter. But you're good. But anyway, that was the conclusion. This is the way we have chosen to do the BBF brick, as we call it. We want to, again, low weight, easy to install, sustainable facing brick slips, well-documented performance. But the thing is that we are in the GRC business. We really want to lower that weight. We really want to lower the impact. We really want to be GRC. It's unique. Nobody can do what GRC can. And we feel it a kind of a punishment to put this extra load on top without any particular gain on it. So that brings me just to very shortly introduce the second one, which is, it is launched. We are discussing for some projects. We have carried out many experiments, which is actually just a replica. You can call it a replica, or you can do whatever you want to design your own brick, design your own joint. It's basically GRC all the way through. We have found a technique for the surface texture. We have found a surface texture for the jointing system. How to manage the coloring. We are playing with the different tones, so we get some reality and so on. That is really what we believe should be, at least from GRC point of view, and meeting the commitments of GRC to the society. It's the lowest way. It's the lowest use of materials. It has all the gains that we want to keep. And we think we are doing pretty well, and architects are quite interested when they see it and surprised that it actually is possible to do. We do it all in a wet-on-wet process. It's a one continuous process, so there is nothing. I mean, we are playing with materials of the same components, and they are all wet when they meet each other. So there's nothing really dangerous we do in the process. It's just about managing the aesthetics of the surface, so it actually looks like something you would like to see. And just to put it down, I mean, the weight, we go down to 45 kilo per square meter, because we can do now elements as we know them with the same type of fixing, exactly the way we do GRC now, we can do now. It's no more different than having a Reclimat or whatever. It's just a little extra weight on the surface. Everything we design as we do with everything else now. And the CO2 equivalent has been reduced. If you remember, it was around 27 for the lowest we could get with real brick slips. Now we're getting down to 20 to 22 kilo per square meters. And that we believe is something that is worth offering to the market. And we believe is within the whole rationale of GRC, having something that is unique and should be selected for that reason. And just final statement. Use us, test us, try us. We are willing to try everything. Okay.